All right, welcome back to day 9 of learning OpenGL. We are on the materials chapter of the lighting section. So this is how far along we are. So this is the last chapter that we did. We implemented the Phong lighting model. We implemented a directional light, and the material has diffuse, ambient, diffuse, and specular lighting. So far, so good. So in this chapter, we're going to be learning about materials. In the real world, each object has a different reaction to light. Steel objects are often shinier than a clay vase, for example, and a wooden container doesn't react the same to light as a steel container. Some objects reflect the light without much scattering, resulting in small specular highlights, and others scatter a lot, giving the highlight a larger radius. If we want to simulate several types of objects in OpenGL, we have to define material properties specific to each surface. In the previous chapter, we defined an object and light color to define the visual output of the object combined with an ambient and specular intensity component. When describing a surface, we can define a material color for each of the three lighting components, ambient, diffuse, and specular lighting. By specifying a color for each of the components, we have fine-grained control over the color output of the surface. Now add a shininess component to those three colors and we have all the material properties we need. So these properties are already that we did in the basic lighting section. So the ambient light, the diffuse light, and the specular light. And then of course the specular light also takes in the shininess value. So yeah, if you increase the shininess, you can see as we're doing here. So those are the four properties that we need to define a material. And then here it's showing some examples. If we vary these properties, the values of these properties, we can simulate different types of materials. In the fragment shader, we create a struct to store the material properties of the surface. We can also store them as individual uniform values, but storing them as a struct keeps it more organized. We first define the layout of the struct and then simply declare a uniform variable with the newly created struct as its type. As you can see, we define a color vector for each of the Phong lightings component. The ambient material vector defines what color the surface reflects under ambient lighting. This is usually the same as the surface's color. The diffuse material vector defines the color of the surface under diffuse lighting. The diffuse color is just like ambient lighting, set to the desired surface's color. The specular material vector sets the color of the specular highlights on the surface, or possibly even reflect a surface-specific color. Lastly, the shininess impacts the scattering radius of the specular highlight. So those are the four values that we are going to wrap up in a single struct. We're going to call that struct material. When these four components that define an object's material, we can simulate many real-world materials. A table as found at DevernayFree.fr shows a list of material properties that simulate real materials found in the outside world. The following image shows the effect several of these real-world material values have on our cube. Okay, so we can just set these values directly, plug these values directly into our material, and we can actually simulate these materials. That's pretty cool. Moving on, as you can see, by correctly specifying the material properties of a surface, it seems to change the perception we have of the object. The effects are clearly noticeable, but for more realistic results, we will need to replace the cube with something more complicated. In the model loading chapters, we'll discuss more complicated shapes. Yeah, that's actually the next chapter, which I'm super excited about. Figuring out the real material settings for an object is a difficult feat that mostly requires experimentation and a lot of experience. It's not that uncommon to completely destroy the visual quality of an object by a misplaced material. Let's try implementing such a material system in the shaders. So this is what we're going to need to do. First, we need to create this in the fragment shader. We need to create a struct. All right, this struct will have vec3 ambient, vec3 diffuse, vec3 specular, and a float of shininess. Okay, and then we're just gonna create a material uniform of this type. Let's just move this up. Okay, so now we need to set these values from our C++ code. And to use this, we're gonna use this just like we used our actual stuff. So here we have the ambient strength, but rather than setting it to some constant value, we're gonna use material dot ambient. Similarly, for the diffuse, what we're gonna do, okay, the normal is the same. Then we have the light direction, that's not gonna change. Then we have the diff, which is the max, the dot product between normal and the light direction. Again, that's not going to change. And then diffuse, here it's multiplying the diffuse with the material dot diffuse. So that way we can actually specify how much diffuse we want it to be. Okay. Diffuse times material dot diffuse. I guess similarly we are calculating the specular, but then we're multiplying it by material dot specular. Okay, so we're not going to use specular strength here. Rather, what it's doing is it's rather than doing it power of some constant value, we're going to do power of shininess. So that's going to control our shininess. And then this vec3 specular. Yeah, we have a specular strength with it, which is just some constant value. We don't need this either. We're going to multiply our light color by spec times our material dot specular. So functionally it's the same thing, but rather than multiplying these things by some constant value, we are multiplying it by a uniform so that we can control these uniforms from our C++ code. And that the rest of the stuff is the same: ambient, diffuse, specular, ambient, diffuse, specular. Okay, it doesn't have object color here, which is interesting. I suppose the color will actually be baked into the material. So we can actually define the color through our diffuse. So we don't need the object color uniform anymore. I guess we can just get rid of that. As you can see now, access all the material struct properties wherever we need them, and this time calculate the resulting output color with the help of the material's colors. Each of the object's material attributes are multiplied with their respective lighting components. We can set the material of the object in the application by setting the appropriate uniforms. A struct in GLSL, however, is not special in any regard when setting uniforms. A struct only really acts as a namespace of uniform variables. If we want to fill the struct, we will have to set the individual uniforms, but prefixed with the struct's name. So rather than creating a struct in C++ and then setting it all at once, what you have to do is use the name of the struct dot and then the name of the property. Okay, so this is the lighting shader inside our main. Yeah, I'm setting the object's color. We don't have that uniform anymore, so let's get rid of that. And then I guess we can just, oops. We can just set all these. We set the ambient and diffuse component of the color we'd like the object to have, and set the specular component to the object to a medium bright color. We don't want the specular component to be too strong. We also keep the shininess at 32. So 32 is what we already had, so that's not going to change. And then this is where we are defining the color. The ambient and the diffuse are the same color here. And then we have specular, which is 0.5, 0.5, 0.5. Okay, so this is what we should see, hopefully. Yes, this is almost exactly what we have in the screenshot. It doesn't really look right though. Lighting properties. The object is way too bright. The reason for the object being too bright is that the ambient, diffuse, and specular colors are reflected with full force from any light source. Light sources also have different intensities for their ambient, diffuse, and specular components respectively. In the previous chapter, we solved this by varying the ambient and the specular intensities with a strength. Yeah, we had the strength values, but we removed those. We want to do something similar, but this time by specifying intensity vectors for each of the lighting components. If we visualize light color as a vec3 1, so it will be 1 1 1, the code will look like this. Okay, so we have the ambient color basically, but it's full intensity. So it's kind of like multiplying it by a like what, like 3 of value 1. So each material property of the object is returned with full intensity for each of the light's component. These vec3 1 values can be influenced individually as well for each light source, and this is usually what we want. Right now the ambient component of the object is fully influencing the color of the cube. The ambient component shouldn't really have such a big impact on the final color, so we can restrict the ambient color by setting the light's ambient intensity to a lower value. So all we have to do is just multiply it by a vec3 of 0.1. So this is our ambient. Suppose that's it. Yeah, so now it's back to how it originally was. Okay. We can influence the diffuse and the specular intensity of the light source in the same way. This is closely similar to what we did in the previous chapter. We could say we already created some light properties to influence each lighting component individually. We'll want to create something similar to the material struct for the light properties. Okay, so now we want to specify all the light properties. So the position, right now we're just sending the position alone, light position. We can wrap that in a struct as well, and also send more information like the ambient, diffuse, and specular intensity. A light source has different intensity for its ambient, diffuse, and specular components. The ambient light is usually set to a low intensity because we don't want the ambient light to be too dominant. The diffuse component of a light source is usually set to the exact color we'd like a light to have, often a bright white color. The specular component is usually kept at vec3 1, shining a full intensity. Note that we also added the light's position vector to the struct. Just like with the material uniform, we need to update the fragment shader again. So wherever we are multiplying the light color, rather than using that, we're going to use light dot position, and the color will come from the diffuse and the ambient. Okay, so let's just create the struct. There we go, and then we create a uniform of that type. Okay, we already read that. Just like material uniform, we need to update the fragment shader. So the ambient here is the light.ambient, rather than setting it to some constant value, we're going to do light.ambient, then multiplying it by material.ambient. And I guess rather than having a light color, this color information will be inside the light ambient value. So we don't need the light color and light position uniforms anymore. Okay, for the diffuse, we have light.diffuse. Don't need light color anymore. Light.diffuse, and then similarly multiplying it by diffuse, the diff that we calculated, and material.diffuse. Cool. Same for the specular. Rather than having light color, we're gonna do light.specular times the spec times material.specular. Cool. We then want to set the light intensities in the application. So similarly, like we set the material properties, we're going to set the light properties. So we're not setting the light color and light position. We can just do this. Let's try that. Okay, where are we? Darn it, I'm not seeing it. Yeah, I think there's some error. Light pause undeclared identifier fragment shader not compiled. Yeah, I think we're using light pause U after we deleted it. Yeah. So we don't have light pause anymore. We need to do light dot position right here. And then, okay, we're not setting light dot position. Where are we doing that? Okay. And we're back. Okay. For some reason, it did not show that we need to set the light boss. Anyway. Now that we modulated how the light influences the object's material, we get a visual output that looks much like the output from the previous chapter. This time, however, we got full control over the lighting and the material of the object. Changing the visual aspect of objects is relatively easy right now. Let's spice things up a bit. So different light colors. So far we used light colors to only vary the intensity of their individual components by choosing colors that range from white to gray to black, not affecting the actual colors of the object, only its intensity. Since we now have easy access to the light's properties, we can change their color over time and get some really interesting effects. Since everything is already set up in the fragment shader, changing the light's color is easy and immediately creates some funky effects. Okay, see that here we're changing the light's color. As you can see, a different light color greatly influences the object's color output. Since the light color directly influences what colors the object can reflect, as you may remember from the colors chapter, it has a significant impact on the visual output. We can easily change the light's color over time by changing the light's ambient and diffuse color sign. Okay, so here we're just setting it directly to some value, but we can also do GLMX3 light color, and then it's using sign to change that, and then setting it to this uniform. Okay, let's just try that. Right, it's pretty cool. And that's it. That was actually quite a small chapter. We just completed it in 24 minutes. I think we have time to move on to the next chapter. In the previous chapter, we discussed the possibility of each object having a unique material of its own that reacts differently to light. This is great for giving each object a unique look in comparison to other objects, but still doesn't offer much flexibility on the visual output of an object. In the previous chapter, we defined a material for an entire object as a whole. Objects in the world, however, usually do not consist of a single material, but of several materials. Think of a car. Its exterior consists of shiny fabric. It has a window that partly reflects the surrounding environment. Its tires are all but shiny, so they don't have specular highlights. And it has rims that are super shiny. If you actually washed your car all right, the car also has diffuse and ambient colors that are not the same for the entire object. A car displays many different ambient diffuse colors. All by all, such an object has different material properties for each of its different parts. So the material system in the previous chapter isn't sufficient for all but the simplest models. So we need to extend the system by introducing diffuse and specular maps. These allow us to influence the diffuse and indirectly the ambient component, since they should be the same anyways, and the specular component of an object with much more precision. What we want is some way to set the diffuse colors of an object for each individual fragment, some sort of system where we can retrieve a color value based on the fragment's position on the object. This should probably all sound familiar, as we've been using such a system for a while now. This sounds just like textures we've extensively discussed in one of the earlier chapters, and is basically just that, a texture. We're just using a different name for the same underlying principle, using an image wrapped around an object that we can index for unique color values per fragment. In lit scenes, this is usually called a diffuse map. This is generally how 3D artists called them before VBR. Since a texture image represents all of the object's diffuse colors. To demonstrate diffuse maps, we're going to use the following image of a wooden container with a steel border. Let's just grab that. Okay, using a diffuse map in shaders is exactly like we showed in the texture chapter. This time, however, we store the texture as a sampler 2D inside the material struct. We replace the earlier defined vec3 diffuse color vector with the diffuse map. Keep in mind that sampler 2D is so-called opaque type, which means we can't instantiate these types, but only define them as uniforms. If the struct would be instantiated other than as a uniform like a function parameter, GLSL could throw strange errors. The same thus applies to any struct holding such opaque types. We also remove the ambient material color vector since the ambient color is equal to the diffuse color anyways. Now that we control ambient with the light, so there is no need to store them separately. Okay, so we're just gonna have a texture, a sample 2D for the diffuse, and we're gonna use the same texture for ambient as well. That means we don't need ambient and diffuse separately. We're just gonna have a sampler 2D diffuse. Nope. Yeah. Okay. If you're a bit stubborn and still want to set the ambient colors to a different value other than the diffuse value, you can keep the ambient vec3, but then the ambient color would still remain the same for the entire object. To get different ambient values for each fragment, you'd have to use another texture for ambient values alone. No, sir, we don't want to do that. Note that we are going to need texture coordinates again in the fragment shader, so we declare an extra input variable. Then we simply sample from the texture to retrieve the fragment's diffuse color value. Okay, vec3 diffuse, and then we have the light diffuse, which is this, and the diff that we calculate, and then this time we have to do texture material.diffuse and then give it the texture coordinates obviously, and it will give us a vec3. So for the diffuse, where's the diffuse? Okay, so we can directly multiply it by material.diffuse. We have to get the material.diffuse, get the texture out of it, texture coordinate, and then we'll get a vec3. Also, don't forget to set the ambient materials color equal to the diffuse materials color as well. So this is also going to be same. Rather than material.ambient, we're going to do the same thing. And that's all it takes to use the diffuse map. As you can see, it is nothing new, but it does provide a dramatic increase in visual quality. To get it working, we do need to update the vertex data with the texture coordinates, transfer them as vertex attributes to the fragment shader, load the texture, bind the texture to the appropriate texture unit. The updated vertex data can be found here. The vertex data now includes vertex positions, normals, and texture coordinates for each of the cube's vertices. Let's update the vertex shader to accept texture coordinates as a vertex attribute and forward them to the fragment shader. Okay, let's actually first take our data and update it here. Cool. We have the position, the normals, and we've added the texture coordinates. Great. And then we need to change the fragment shader to the vertex shader. We have a pos, a normal, and we also need to do what is this, a text coord. Okay, and then we're just passing it on to the fragment shader. Text coords is equal to a text coords. Be sure to update the vertex attribute pointer of both VAOs to match the new vertex data and load the container image as a texture. Oh, we're gonna have to go back. Okay, I need to plug in my charger. Just give me 1 sec. All right, we're back. So first of all, we need to change our attributes. Okay, what is this? Stride. One, two, three, 4, 5, 6, 7. Okay, it's gonna be 8 now. All right. Size of float. Yep, it's gonna start from the beginning. This will be 3 over, and then this will be 6 over. Okay. I think that's all we need to do. And then enable it. So now we actually need to pass some data. We actually need to make the texture. Okay. I don't think I remember how to do that. We're gonna have to go back to the textures chapter. Darn it. Okay. Yep, we already have STBI. Yeah, we already have STBI library loaded, so that's fine. We need some channel and stuff. Okay. And STBI load will just load our data. Let's give that a try. Do I have the image? Okay, we have this container. We need a different image. Container 2. Okay, let's try to load container 2.jpg. Okay, this is a PNG. PNG. Cool. And then we need to generate a texture. So we'll do that. JSON texture takes the first arguments, how many textures you want to create, blah blah blah. And then we need to bind the texture. Now that the texture is bound, we can start generating a texture using a previously loaded image. Textures are generated with GL text image 2D. Okay. So we're passing in the width, the height, and the data that we have. And then we want to generate the bitmaps. All right. And then you want to free the data. Okay. So we've done this. We have our texture. We generated the texture. We bound it. Okay, we need to set some parameters. I don't know if it sets some default parameters or not. I'll just do it here. And then the width and the height. This is fine. You can do it before as well. I actually might want to see if it's successful or not. All right, let's see if it actually loads it or not. No. Okay, we have some problems, I think, with our shader not passing it correctly. It's fine, we'll deal with that later. Um, 8x coords, untickled identifier, a sign cannot convert from a high b float to varying to component vector of high b float. So this is inside vertex shader. I'm doing something wrong. Not sure because I'm not setting it to something yet. We'll check that later. Okay, so our image is loaded. Then to apply the texture, we already have added the texture coordinates. We already did all of this stuff. Okay, we added this. GL bind texture. Then we have the data, and then we're setting it here. Okay. Something's not right. We're taking the northern frag, but I don't think we're taking text coords. Because we are using it here. Okay, let's try that. Nope, still something is wrong. So in the vertex shader, it's saying 8x coords is undeclared identifier. Okay, this is 8x coord. What the hell? Let's try again. Okay. Yeah, this is not good. Our light is using the same shader. That's the problem. It's using the same vertex shader. Yeah, might as well change that. Let's create a separate vertex shader for that. So we have unlit fragment shader. Let's do unlit shader.vs and add it here. Okay, it's not gonna have this stuff. And then just as we created a separate fragment shader for this for our light, Okay, let's try that. Okay, now we have problem the fragment shader. Texture no matching, overloaded, function found using implicit conversion. Function is not known, no matching, overloaded, function found. Okay, texture is not an actual function, it seems. And it's also saying failed to load texture. Okay, one problem at a time. Let's see. So what is it showing us? Texture. Well, it is showing a texture as a function. It's passing the sampler 2D and the texture coordinates. That's exactly what we're doing in our fragment shader. We have texture. We're passing in our sampler 2D, are we? Material dot diffuse. Yeah, we are. And our texture coordinates. Okay, let me just not do this for now. So it's saying we have a syntax error, which I probably did make some error here. Yep. Okay, again some syntax error. What's happening? Again some syntax error. Text cohorts has different type width across different shaders. Okay. Text cohorts. This is text cohorts, a text cohorts. And then text cohorts is a vector 2. And then we're setting the value here. And then it goes to fragment shader. Okay, it's supposed to be a vector 2 here. Yeah, we have our cube back, but our light source is still mangled. Let's try and fix that. I think we're not setting the attributes correctly. Because we didn't change those, we need to change that as well. Yeah. So here we're setting this to 3, but I guess this will be 8 because now the stride will be 8. Okay. Yep, our light cube is back. Now, okay, let me just check if texture is loading now. The texture is still not loading, so we need to fix that now. What am I doing wrong? Kind of weird. We have container.jpg and container2.png. Maybe I'm okay. Yeah, I'm setting it to jpg. Let's try that. And yeah, that gets rid of the error. So I guess we can use it now. multiplied by our texture. Okay, not what I was hoping, but it's something. Is the texture coordinate incorrect or something? Material or diffuser? We're not setting this. We haven't set this yet. Yeah, we have our texture. Where are we setting our texture? It's a uniform. Okay, let's look at the source code directly. Okay, it doesn't call our texture. This is our STB image. This is our texture. We're doing the same thing, loading it. This is the data, and then you're freeing the data. And binding it with, say, texture. So in here, it's binding it right before we're using our shader. Let's try that. Still nothing. I'm missing something. Texture coordinate is set. We're doing this correctly. 0, 3, and 6. Stride is 8. 0, 1, 2, 0, 1, 2, 3, 3, and 2. I think this is all fine. Zero, 1, 2, 0, 1, 2, 3, 3, and 2. Stride is 8, 0, 3, and 6. Yep. Okay, let's just try container.jpg. Okay, JPG is working. Maybe I'm doing something wrong here. Is this RGBA? Internal format. Let's try this. Still nothing. GL text image 2D, GL text image 2D. Why am I doing it twice? All right, we're in business. So it was just a matter of whether it's a JPG or a PNG, because PNG has alpha value as well. So you need to make sure you supply the correct format here. Okay. That was kind of anticlimactic. Cool, 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 cool. Now that we have the texture, we're using it for our diffuse as well as our ambient. We can move on. And that's all it takes to use a diffuse map. As you can see, it is nothing new, but it does provide a dramatic increase in visual quality. I think I already read that. The ability vertex data can be found here. The vertex data now includes the vertex position, normal, and the texture coordinates. We already did this, and then we have the specular map. You probably noticed that the specular highlight look a bit odd since the object is a container that mostly consists of wood, and wood doesn't have specular highlights like that. We can fix this by setting the specular material of the object to vec3 0, but that would mean the steel borders of the container would stop showing specular highlights as well. Right, I think we have someone in the chat, Cubits8513, saying, hey, how's it going? It's going great, thanks. Okay. So yeah, it's basically suggesting rather than setting the specular value to some constant again, we can actually use a texture for that as well. We can also use a texture map just for specular highlights. This means we need to generate a black and white or colors if you feel like it texture that defines the specular intensity of each part of the object. And then this specular will be using this map. Let's just grab that as well. Varying intensity. This is a problem that sounds familiar. Coincidence? I think not. Okay, we're going to use this texture. The intensity of the specular highlight comes from the brightness of each pixel in the image. Each pixel of the specular map can be displayed as a color vector, where black represents the color vector vec3 0, the gray represents 0.5 obviously, and then white will represent 1. In the fragment shader, we then sample the corresponding texture color value and multiply this value with the light's specular intensity. The more the white a pixel is, the higher the result of the multiplication, and thus the brighter the specular component of an object becomes. Because the container mostly consists of wood, the wood as a material should have no specular highlights. The entire wood section of the diffuse texture was converted to black. Black sections do not have any specular highlights. The steel border of the container has varying specular intensity, with the steel itself being relatively susceptible to specular highlights while the cracks are not. Technically, wood also has specular highlights, although with a much lower shininess value, more light scattering, and less impact, but for learning purposes, we can just pretend it doesn't have any specular highlight of it. Using tools like Photoshop or GIMP, it is relatively easy to transform a diffuse texture to a specular image like this by cutting out some parts, transforming it to black and white, and increasing the brightness or contrast. Are you a programmer? You probably are, but I'm curious about your experience. Yes, I am actually a programmer. I have some like 2 years of experience in like Unity and like the Godot engine. I don't have any professional experience in Godot. I use that for mostly personal projects. Yeah. Moving on, sampling specular maps. A specular map is just like any other texture, so the code is similar to the diffuse map code. Make sure to properly load the image and generate a texture object. Since we're using another texture sampler in the same fragment shader, we have to use a different texture unit for the specular map. So let's bind it to the appropriate texture unit before rendering. All right, it's doing something like lighting shader dot set it material dot specular and setting it to 1. GL active texture, GL texture 1, and then GL bind texture. Okay, bind this specular. So let's actually first load the data for this, which is just going to be the same as we did for the diffuse map. So this will be texture 1, and texture 2. Rather than container.png, we need a different image. Okay. There's our specular image. Texture 2, okay, let's call this texture 2. We have read the data. We need to define it again. We can just use the same variable. Down here. I see. I decided to go deeper into how the engine works. Yeah, that's right. Okay. So we're loading the second image data here, and then we are passing it. We're doing GL text image 2D. This is also an RGBA, so that's fine. Generating the maps with this. Wait a sec. Okay, so we have this bound already, so it should be stored in texture 2. I went basically the same route like 2 years ago. This is a deep rabbit hole. Yeah, that is right. This is a very deep rabbit hole. Like from OpenGL, like basically you can go anywhere. You can maybe go into Vulkan or maybe DirectX, whatever you want to do. So our second texture will just be similar to the first texture. Where is that? Yep. So we're binding this. Not sure if it'll be like this, or do we need to first lighting shader dot set int specular. So lighting shader, good. Wait, what did it do here? I decided to create, I guess, did everything from scratch. That's not either in C++ or in OpenGL, so I wrote my own math level. Yeah, you can actually go even lower level than this. You can create your own libraries. Like I'm using GLM, but obviously you can create your own math library. All right, let's just focus on this for now. Lighting shader dot set int, and then it's doing material dot diffuse to 0. We already did this. Be sure to update the vertex attribute pointers of both VAOs to match the new vertex data and load the container image as a texture. For rendering the cube, we want to assign the right texture unit to the material.diffuse uniform sampler and bind the container texture to this texture unit. I mean, I didn't do that, but it's still running for some reason. Okay, now it's using the second one. Okay. I think I need to go back to the texture chapter. And see how it was loading two textures. You probably wondered why sampler2d variable is a uniform if we didn't even assign it some value with GL uniform using GL uniform 1i. We can usually assign a location value to the texture sampler, but we can set multiple textures at once in a fragment shader. This location of a texture is more commonly known as a texture unit. The default texture unit for a texture is 0, which is the default active texture unit, so we didn't need to assign a location in the previous section. Note that not all graphics drivers assign a default texture unit, so the previous section may not have rendered for you. The main purpose of texture units is to allow us to use more than one texture in our shader. By assigning texture units to the samplers, we can bind the multiple textures at once as long as we activate the corresponding texture unit first. Just like GL bind texture. Yeah, I had totally forgotten about this. So this is a good refresher. Rather than just binding it directly, we actually have to first set a texture, set an active texture unit like this. Not sure if this is good enough, but we can try. After activating a texture unit, a subsequent GL bind texture call will bind the texture to the currently active texture unit. Texture unit GL texture 0 is always by default activated, so we didn't have to activate any texture unit in the previous example. We still, however, need to edit the fragment shader to accept another sampler. This should be relatively straightforward now. Okay, yeah, this is what we need to do here. We have this. We need a sampler for the specular. The final output color is now a combination of the two texture lookups. So I think that's all I needed to do. That way we have material.sampler2d .specular, which is a sampler2d, and then we can just use that in specular. Yeah, the same way we used our diffuse map. So this is our specular. We can't just multiply directly, we have to get the texture like that. Okay, hopefully this will work. Yeah, I think this is working. Not sure. So I'm doing texture material.specular. Yeah. We don't need these parentheses anymore. Light.specular spec, and then we're getting the specular texture. Like this is much more pronounced here, but I can't tell if it's working or not. If you want to make actual progress, I would not recommend doing that, though I did learn a lot by implementing all that linear algebra. Yeah, that's true. Like going that deep is mostly just for like learning purposes. If you want to actually make a game, it doesn't make much sense to implement your own math library, like unless you have a very specific need for that. Anyway, okay, so either this works that I can't tell, or it does work. Because this feels like even the wood has some specular. Not sure. This is exactly what I did. And if we just show it here, you can actually see that it's loaded correctly or not. I think that's the issue. It's not. It may not be loaded correctly. Yeah, it's still loading the diffuse map into the specular sampler 2D for some reason. Okay, lighting shader, which is this shader. We're setting the int material.specular, which is this one. Oh, I guess you need to tell it which one is 0 and which one is 1 essentially. Okay. Because it doesn't know. So we'll just need to go here. And yeah, we're doing material.ambient. That's fine. We don't have material.diffuse anymore as a vec3. So it will just be set int material.diffuse and it will just be 1. And specular is also a sample 2D now. So this will also be set int. Then we're gonna set this to 1. Okay, we're gonna set this to 0 and this to 1. Let's see. Okay, yeah, now it's loading it correctly. So we can go back to using our diffuse map here. And yeah, now that looks correct. Okay, cool. So we're done with that. Using diffuse and specular maps, we can really add an enormous amount of detail into relatively simple objects. We can even add more detail into the objects using other textures like normal bump maps and or reflection maps, but that is something we'll reserve for later chapters. Show your container to all your friends and family and be content with the fact that our container can one day become prettier than it already is. True. Fool around with the light sources, ambient, diffuse, and specular vectors and see how they affect the visual output of the container. Try inverting the color values of the specular map in the fragment shader so the wood shows specular highlights. Yeah, this is fine. Try creating a specular map from diffuse texture and use feature colors, black and white. Also add something they call an emission map, which is a texture that stores emission values per fragment. Emission values are colors an object may emit as if it contains a light source itself. This way an object can glow regardless of the light conditions. Okay, the stream has been going on for like 1 hour 12 minutes, so I think I'm gonna end the stream here. Though I did learn a lot by implementing all the linear algebra, I think it does work. Oh, and there's a Visual Studio extension to add syntax highlighting for GLSL. Would highly recommend installing that. Yeah, I actually was looking into that, but I couldn't get it to work. I'll actually try again because doing it like this is kinda masochist. So yeah, I'll try installing that again and trying to get that to work. Yep, thanks for the advice. Okay, so next week we're gonna be doing light casters. So I guess we're gonna do like spotlights and point lights, yep, and light attenuation. So that's gonna be an interesting chapter. See you guys next week. Bye.